Okay, I'm going to talk on additional topic on CAN extensions, and I'll continue the talk of Arsenis talk on CAN extensions. First of all, I recall some basic definitions and properties and prove something. Okay, we start with a definition. I recall that for given a functor f from category C to category D, E, and for a functor from C to D, we have the following diagram like this. We say that we have a left CAN extension, and we'll use this notation. If we have the following identification of this diagram and this one, for all natural transformation gamma, each natural transformation gamma factors through natural transformation eta from F to composition of this of left CAN extension and functor K, such that we have the identifications or identification of these diagrams C to E and like this, and for all functor sorry. For all functor G, we have a natural, unique natural transformation alpha, and we have a natural transformation eta, such that we have the identification of these diagrams. Okay. And dually, we can define a right CAN extension, and I give some example which was mentioned in Arsenis talk. I recall something. This is consider functor f with consider left CAN extension along functor K, which is a functor onto category which consists of one object and one morphism, and then we obtain in this situation the following identification. Which says that if we have two objects E and E prime objects in the category E, then we have the following. We can notice that delta E is a cone, and we have a morphism between cones, and for such two objects, we have the following. We have natural transformation eta by default, and there is a unique natural transformation alpha between delta E and delta E prime and delta E prime. And what does it mean? It means that we have for any two objects C1 and C2 morphisms between cones. This one and also this one. Sorry. And this is a definition of co-limit. Co-limit of functor f equals just left Kahn extension of f along k, and we evaluated at object one in this category. Okay. And dually we can define, we can derive that limit is a right Kahn extension, and okay, now we will formulate a proposition, important proposition. Right Kahn extension and left Kahn extension are functors. We have this map, and also this is quite easy, and we will prove it. Okay. First of all, we will notice that the following diagrams are equivalent. If we have this one, consider natural transformation alpha between functor g and functor f. Okay, and we have here natural transformation functor g, and also we have natural transformation epsilon g. Epsilon g is a unit of this right Kahn extension. We can consider this functor, and we may consider right Kahn extension of this functor along k, and epsilon is a natural transformation from definition of right Kahn extension. Default, it is a default natural transformation in definition. Okay, and then this diagram is the same as this one. We can use a universal property of right Kahn extension, and then we obtain the following. We have obtained factorization like this, and this is right Kahn extension of f along k, and we have a natural transformation alpha prime, and this natural transformation exists because of universality of right Kahn extension. Okay, and thus we can conclude that right and left conextensions are functors. Consider following sequence of natural transformation H to G to F, and let it be beta and alpha. And then I can write the following qualities of diagrams. We have such diagram. And this is a right conextension of F along K. This is a right conextension of G along K, of course. And last is a right conextension H along K. And we have natural transformations between these functors. Denote it's alpha prime, beta prime. And then we can compose these two cells by means of the following quality. And we have these relations C2 C2E by means of G, F, and now we have composed this. Oh, sorry, and also epsilon F. We compose these two cells. We compose these two cells, and therefore we should add. We should add functor G here. I use this relation, and K, and also and here we have epsilon G natural transformation, and here alpha. Okay, and in the same way we can compose these natural transformations, and thus we obtain following diagram. This is a run H along K. This is F, G, H, and here we have natural transformations alpha, beta, and epsilon H. And what does it mean? Thus, we have that right conextension of composition of the natural transformations alpha and beta along K equals composition of natural transformations alpha prime and beta prime, and it means that this is a functor. Okay, and and now I want to formulate the following result, important theorem. Important theorem. If the conextensions if the Khan extensions exist for all f, for all functors f between categories C and E, then we have the following adjunctions. Denote like these functors between categories. For example, this one is functors between categories C and E, and so on. Okay, we can notice that this map is a precomposition with functor K, and this functor is left joined to right Khan extension functor and the left, and it is right joined to the left left Khan extension functor. Okay, let's prove this. For any pair which consists of the pair of the functor G and the natural transformation gamma, such that we have the following diagram. With natural transformation gamma, then by unit lemma, we know that this we know that we have this natural transformation gamma star from this one to to this, and this natural transformation between functors, this notation means that we consider functors which if we have some functor h, we can take this functor to h, and we will obtain natural transformations between functors g and h, and also this. This circle is composition of the functors. Okay, and we have identification of this natural transformation, and the set of natural transformation gamma, which is a natural transformation between functors f and g with g composed with k. Okay, and we can define gamma star like this. Gamma star of alpha equals the composition of alpha and gamma. Alpha is natural transformation between G and H, and we can form this map. Okay, and then if we take G equals left Kan extension of F along K, then we have isomorphism, the following isomorphism eta star between natural transformation ln F along K and natural transformation F and G composition with K. And this is isomorphism because of universality of Kan extension, obvious isomorphism. And this isomorphism says us that tells us that we have an adjunction. Okay. In the same way, we can prove that there is a adjunction like this for right Kan extension. Okay. And now, and we can write some thesis. The left adjoint to any precomposition factor is a left Kan extension functor this follows from uniqueness of adjoint functor, and this is great. Okay, as example, this is an example from model category left and right derived functors. Left derived functor over a functor F between model categories M and N is just right Kan extension. Right Kan extension along localization functor. Gamma from M to M, and such that we have the following equality of diagrams. for any functor G with natural transformation psi from G gamma to F equals sorry. There exists factorization. There is a unique sigma natural transformation, and there is a LF derived functor of f from m to n, such that we have the following identification. Okay, and in the same way we can define a right derived functor. And I want to give now definition of I want to recall the definition of the preserving extensions. Definition. I recall that functor L from E to F preserves left can extension of a functor f along k with a unit eta if we have the following identification of the diagrams. This just means that we that L preserves left can extensions that is a composition L with the left can extension of F along K is a left can extension over L composed with the F along K. That is with the co-unit L eta. I can call co-units as a unit and unit as a co-unit, but I suppose that it's okay. Okay, and we want to prove the following interesting theorem. Which says that left left adjoints preserve left conextensions. And dually right adjoints preserve right conextensions. Okay. Let L from E to F be left adjoint to the functor R from F to E with the unit the unit in the sense of adjunction. Unit E from identity functor to the composition and co-units. New from the composition of L and R to the identity functor of the category C. Okay, and hence we should prove the universal. We should prove the universal property, and we consider consider functor H between D and F and functor G between D and E thus from the definition of adjunction, we have the isomorphism, bijection. Natural transformations between these functors is one-to-one to these natural transformations from G to R, H. And thus we can write for the following. Consider natural transformation between these functors we move L like this, and we will have the following bijection. And after that, we use the statement which we proved before. This is a theorem number 1, and we can change this functor to a joint functor. and we will have a precomposition. Precomposition with K. F to R H K. And also we move like this, and hence we obtain that natural transformation between this functor and H and L, F, and HK are isomorphic, and hence we can conclude that by a universal property of the left Kahn extension, we can conclude that this functor is the same as this one. Okay, and therefore we obtained the result, but we will omit details of finding the unit and the unit of the extension. It is so boring. Okay, and now we can consider this example. Consider the forgetful factor U from the category of topological spaces to the category of sets, and it has both left and right adjoints. What is a description? We can describe in the following way. The functor D from set to top assigns a set the discrete topology, and we have a factor I from set to top, and this factor assigns a set the indiscrete topology. Okay, and we now have the following diagram. Top two sets. We have adjoints I and D, those K and 2 . two CAN extensions. Okay, and thus by this theorem we obtain that this factor this factor preserves both left and right joins. Okay, and now we can make the coffee break or something. And now I want to formulate the following important result, following theorem, which tells us that let R, we have a factor R from C to D, and it has a left adjoint a left adjoint if and only if and only if there exists right if and only if there exists right CAN extension of identity factor in the category C along factor R, and R preserves this right CAN extension. Moreover, when this is case, we have that this right CAN extension is the left adjoint to the factor R, and co-unit map is the natural transformation between this factor, between this composition of the factors and the identity factor is a co-unit of adjunction. Okay, and the diagram in this case let's prove it. Let's prove it. We should we prove first of all in this direction, and assume that L is left adjoint to R with the unit eta from this to this composition, and sorry, I should define what is triangle relations. First of all, I should define this notion. Definition. triangle identities. This is the diagrams which come from a junction between factors L, R, and L, such that we have these identifications between diagrams. We have this parallelogram, quadrilateral, with identity factor R, identity factor from D to D, and factor L, and the natural transformations eta, co-unit, and unit, and this one equals this one. Trivial diagram in which we have a trivial natural transformation, and in the same it's okay. And in the same way, we can define the other triangle identity like this. Equals and also. Okay, these are triangle identities, and these follow trivially from the definition of the junction. Okay, and we will use them in the proof. Okay, assume L and L is right joined to R with the units eta and co-unit epsilon. Then we will prove that we will check the factorization property. Check the factorization property. Consider arbitrary pair consists of the function D from D to C and natural transformation. I'll draw the diagram. Have a diagram like this. And now and now we want to prove that this is actually the Kahn extension, and for do this we should verify factorization property and uniqueness of corresponding natural transformation. We have the following diagram, and with natural transformation gamma, And we want to prove that this factor, this natural transformation factors through the epsilon factors through the epsilon, where epsilon is a co-unit of a junction. Okay, and we have the following identification. This diagram equals this one. We just draw this one, and we add trivial cells, trivial two cells, like this, trivial two cells. This diagram is equivalent to a trivial one, to the by means of triangle identity. Okay, and then we can add this one to the diagram, and thus we obtain factorization. If we look at this piece of diagram, we can find that we have a factorization. We have a factorization. Through epsilon, and thus we obtain as a factorization of the pair H gamma through the pair L epsilon, and we should prove that uniqueness, show that this factorization is unique. To do this, we can consider the following quality of the diagrams. Where alpha is some factorization of gamma. Okay, and we can add the two cell to both sides of this equality, and we will obtain the following. And now we can use the second triangle identity for reduce this diagram, this quadrilateral. Thus, we will have this diagram, this simple, beautiful diagram, and it means that this factorization is unique because we have following identification, where eta and gamma is uniquely determined to cells maps. Okay. Thus, the factorization through eta is unique, and the pair L epsilon is the right Kahn extension of the units of the identity factor along R. And also in the same manner, same way, we can prove that R preserves right Kahn extension of the identity along R, and why it is easy. We can form we can draw this diagram for some natural transformation lambda, and this is the same as the diagram. We can add a quadrilateral which consists of trivial two cells. And after that, we find that R preserves this Kahn extension because of we have the factorization like this. We have we can compose these two cells, and we will obtain a new two cell, and it will be factorization natural transformation between the functor S and the composition of functor L and functor R, and thus we obtain the statement, and uniqueness. So I think I skip the details of the proof, and I will consider other results. Okay, and in the same in the same way, we can obtain other statement. Okay, I've demonstrated some technique which use in this proof, and so we can see that this is simple, and but the proof is so long. Okay, and now we consider the corollaries of this theorem. These statements are well known in category theory, and now we will prove them by means of this technique, these theorems. And the first result is very simple. Very simple. Okay. Theorem number 5, or proposition. Left adjoints preserve colimits, and right adjoints preserve limits. It's an easy statement, but now we apply our powerful technique to prove this. We know, we know that from theorem 3, yes, theorem 3, that left adjoints preserve left can extensions. But colimit is, of course, is the left can extension, as we saw, is the left can extension of functor f just left can extension. Okay, and it's all. And dually we can the same thing. Okay, and the another theorem which says that if we have the following situation, when we have 3 categories C, D, and E, and functors between them, adjoint functors F and G, F prime and G prime, then we can say that a junctions compose. Junction compose. That is we have a junction between F prime F and G prime. Okay. Now we can prove this statement by means of our technique of the CAN extensions. And first of all, we will prove that F prime F is a right CAN extension over this functor along G prime, or we have the equality. Okay, now draw the diagram. Okay. Draw the diagram in which this is an identity factor. Now we have a composition over two factors, G prime and G. And also, we consider arbitrary factor H between categories C and E with a natural transformation gamma from H G prime to this functor, and we should find the factorization, and also we should prove that this factorization is unique. And this is to cell, and we have obviously the following diagram in which we just draw this arrow. And also when we do it, we can factorize the natural transformation gamma into the maps into the cells delta and epsilon prime, where epsilon prime is a unit or co-unit of the adjunction between functors F prime and G prime, and delta and delta is a natural transformation. We use the theorem. We use the theorem above, theorem number 4, which says that a left adjoint is actually a right can extension, and we can use this, and we know now that this f prime is a right can extension over this functor, this identity functor, along the functor g prime, and thus we have the following identity modulo the previous theorem is a trivial fact. Okay, and now we can use a technique of adding trivial cells and removing of it, and we have we add some cells. Cells which follow from I use the triangle identities, and I can form the following diagram. Okay. This one is a trivial quadrilateral. We can add it, and this one is equivalent to a trivial quadrilateral because of a triangle identity. The second to the first to the second, I don't remember. Okay, and we now combine these pieces of the diagrams, this quadrilateral and this triangle, and we will obtain the following. Okay, and now this diagram gives us the factorization of the pair. Sorry, delta. Those also are epsilon. Gives us a factorization of the pair H and gamma through composition of the functors f prime and f. We have the following factorization. And now we should prove that that this factorization is unique. prove it. Consider any natural transformation alpha from H2 to the composition. And we will have the diagram from C to D to prime, and that is and it is alpha. And now we can add some trivial two cells. I use triangle identity and the similar technique. And also natural transformation alpha. Okay, I add this diagram, which exists by means of triangle identities. And now I choose this piece of diagram and compose all of two cells. And as a result, I obtain two cell gamma because alpha is a factorization of gamma, and this composition will equal gamma. And now I can use I can use the following diagram. I can draw the following diagram. And here we have gamma. And here we have H and K. Those. Okay, and now we can notice that this quadrilateral is admits such an interpretation as a triangle identity. We can draw the arrow, and we can find that this quadrilateral we can reduce this quadrilateral. Oh, sorry. Reduce this quadrilateral, and now I redraw diagram. And I draw this arrow, which is just f prime, and we will have here epsilon prime and here delta. And now we can focus on this quadrilateral. And then by triangle identity, this diagram is the same as this one. We we reduce this quadrilateral and obtain this triangle, and we then obtain that this diagram equals this diagram. Oh, this diagram, and thus we have obtained that alpha have a unique factorization. Unique factorization, and thus we've proved theorem. The theorem almost proof, but we should say that we have proved the uniqueness, but we should prove that that this composition is actually can extension. We notice that G prime is is right joint, and then it will preserve the right conextension. G prime preserves the right conextension. The right conextension F prime F. Also, G is right adjoint, and it will and G preserves right conextension G prime F prime F. Thus, the composite functor F G prime preserves the right right adjoint no, sorry, right adjoint right conextensions. Right conextension, right conextension F prime F. And now we can use the theorem number 4. We have verified the conditions of this theorem, we have showed that we have shown that there is this functor, and the composition of functors preserves right Kahn extension of we should change R by composition of factors, and then we will obtain the following result. Okay, I think that's all. Thank you for your attention. Have you any questions?
What are the references for today's talk?
Okay, the reference, this is this is a work of Marina Christina Lehner, and I'll give the source of this work. Okay. This is all concepts. All concepts are Kahn extensions. Kahn extensions as the most universal of the universal constructions by Marina Christina Lehner.
Thank you.
Okay. Okay, thank you. So